Okay, we are discussing about the GATE 1994 ECE paper. This is 5-mark question related to electronics. A typical CMOS inverter has a voltage transfer characteristic as shown in the figure. Evaluate the value of inverter threshold, which is the value of the input at which V0 falls abruptly by VTN plus VTP. Given parameters are beta n is equal to beta p and VTN is equal to 1 volt, VTP is equal to minus 1 volt and VDD is 5 volts. So from this one we can say that one CMOS inverter is nothing but whenever you are applying a input as logic low level, output will be logic high level, and if input is logic high level, output will be logic low level. That is, inversion takes place. But if you are observing, if V input is going to be at low level, by that time logic 0 you are applying, then M1, the transistor M1, which is nothing but NMOS, it will be in the off condition. And M2, if you are observing, M2 is PMOS transistor. For PMOS, logic low level makes it into on condition. So here it is M1 off and M2 on. So the diagram is going to be looking like M2 will be in the on condition and it is connected to V0 and this is VDD, whereas M1 will be in the off condition for the given input V input. So by that time V0 is approximately equal to VDD. So V0 is approximately equal to VDD, which is nothing but high. So whenever input is low level, only one transistor is on condition, that is PMOS, the other transistor NMOS is in the off condition. Similarly, if you are saying V input is going to be at high level, for example, that is logic 1 if you apply M1, which is nothing but NMOS transistor in the on condition, M2, which is PMOS transistor, it will be in the off condition. So by that time PMOS will be off, so that VDD is now no more connected to V0. Okay, but V0 is now connected to ground through NMOS transistor, which is in the on condition. So V0 is approximately equal to 0 volts. So V0 is equal to 0 volts. That is nothing but it will be low level. So this is what the inverter operation. But in any case, if it is at low level, only one of the transistor will be on. If it is even at high level, one of the transistor will be in the on condition, the other will be in remains off. But whenever we are applying an input such that low to high or high to low transitions we are applying, by that time the output is also changes consecutively. So at that time both transistors may be on for a very small amount of time. That is what it is shown on the CMOS inverter transfer characteristics. So here it is, three regions are indicated. First one is nothing but whenever V input is low, V input is low, by that time V output is high, that is first region. Okay, and second region is nothing but whenever V input is high, that is this is high, by that time V0 is nothing but low level. And in between, if there is a transition taking place at input, by that time the output has to change from high to low or low to high. At that time both transistors are going to be in the on condition. This is for a very small amount of time, and whenever both are on, both will be in the saturation region. So at that point, so from these characteristics we can define a logic inversion point, logic inversion point or logic threshold point. Okay, logic inversion point or logic threshold point or switching threshold point. This is going to be called as V inverter, V inversion, or VSP, switching threshold point or V inversion. This is the point at which V input is equal to V output. This is a point from where inversion threshold starts. The meaning of this one is nothing but V input, if it is less than V threshold point, then If V input is less than VSP, then V output is greater than VSP. If V input is greater than VSP, that is threshold point, then V naught will be less than VSP. So from this point onwards, the inverter operation taking place. At the inversion point, input and output are going to be same, and if you apply a small voltage lesser than input, at the time output will be more than the switching threshold point. If the input is more than the switching threshold point, by the time output will be lesser. That is nothing but inversion operation taking place from this point onwards. So this point is called as logic inversion point or switching threshold point, VSP or V inversion. This can be calculated using two ways. One is nothing but graphical way, the other is nothing but analytical way. First you will see how to calculate it graphical way. The graphical way is nothing but on the CMOS inverter transfer characteristics, you have to draw a straight line with slope 1 and it has to pass through the origin. So slope 1 is nothing but y by x is equal to 1. Y axis is output, x axis is input. So output by input is nothing but 1. That is, this straight line gives all the points where V naught is equal to V input. This straight line where it touches the transfer characteristic, that point will be called as switching threshold point or inverter threshold point. This is the point. So it is VSP or V inversion. So at this point input and output are going to be same, and from this point onwards, if you apply lesser than this point, that is if the input is lesser, that is during this portion, output is greater than that one. If the input is greater than this VSP, at that time output will be less than VSP. Okay, so this is VSP can be calculated graphically by drawing a straight line with slope 1 has to pass through origin, and where it cuts the transfer characteristics, that point is going to be called as inverter threshold point, where both the transistors are in saturation region. Now we will see how to calculate this value mathematically. We know that both the transistors are in saturation, so M2 is in saturation and M1 is also in saturation. And how much is going to be the drain current flowing through M2? The same drain current is also flows through M1. So IDP is equal to IDN. Since both are in the saturation condition, both are in series, so that we can write it as IDN is equal to IDP. Drain current of NMOS is equal to drain current of PMOS, and both are in saturation, so that we can write beta n by 2 into VGSN minus VTN whole square is equal to beta n by 2 into VGS beta n into VGS minus VP minus VGS P minus VTP whole square. Whenever you are writing this, VTP is going to be signifying minus 1 volt. Remember that one. So the same equation can be written in this way: beta n by 2 into VSG VSGP minus VTP whole square. By that time this VTP is nothing but only magnitude, so it is going to be specifying 1 volt plus 1 volt. Remember that one. If you are going to say magnitude wise, we are not bothering about the signs. By that time you can write the equation as VSG minus VTP. If you are going to be strictly following the sign, by that time you must write the equation for the PMOS as VGSP. Okay, so from this one we can write it as beta n by 2 into VGSN, that is VGN minus VSN minus VTN whole square is equal to beta P by 2. This is not N, this is P. This is not N, this is P. Beta P by 2 into VSP minus VGP minus VTP whole square. Here VGN is nothing but for NMOS gate voltage. NMOS gate voltage is connected V input. V input is nothing but V inversion. So we can write it as Bn by 2 V inversion minus, otherwise we can write it as VSP beta n into VSP minus VSN, that is nothing but NMOS source voltage which is connected to ground, so it can be written as 0 minus VTN is nothing but we will write VTN only whole square is equal to beta P by 2 into VSP PMOS source voltage. PMOS source voltage is nothing but this is source for PMOS, it is gate for PMOS, it is drain for PMOS. Source voltage is connected to VDD, so this is VDD minus gate voltage of PMOS is nothing but V input. V input is nothing but switching threshold point VSP. VTP we are writing as it is whole square. From this one, if you are going to be solving for VSP, at that time VSP you are going to be getting this equation, square root of beta n by beta p into VTN plus VDD minus VTP by 1 plus square root of beta n by beta p. And for this one, what was the given values is nothing but given beta n is equal to beta p and VTN is equal to magnitude of VTP is equal to 1 volt. So substitute this one, what you will get is VSP is equal to square root of beta n by beta p is 1, square root of 1 is 1 into VTN which is nothing but 1 plus VDD is 5 volts minus VTP magnitude only we are considering 1 divided by 1 plus beta n by beta p is 1, square root of 1 is 1. So this is 5 by 2 which is nothing but 2.5 volts. So the logic inversion point is nothing but VSP V inversion or VSP whose value is 2.5 volts, at which V0 is suddenly drops by delta V0 which is nothing but VTN plus VTP. So the actual answer for this question is 2.5 volts. Thank you.